Okay, welcome to the fourth annual Web Science and Digital Libraries Research Expo. We have a list of 5 students who will be presenting today. The presentations are aimed to be about 15 to 20 minutes. You can ask questions at any point. This is meant to be an overview and interactive, and really just to give you, I guess, an introduction to what a lot of your peers are working on. We'll start with doing the faculty intro. You should probably know everyone, but I'm Michael Nelson. I've been here since 2002. Prior to that, I was at NASA Langley and also got my master's and PhD from Old Dominion. So I've been kicking around the campus for quite some time. Let me see. Obviously, my research areas are in web science, digital libraries, web archiving, social media, and all the areas that you're familiar with that you see on the blog and the Twitter feed and so forth. Let's see. Dr. Weigel, would you like to go next?
Sure. Hi, I'm Michelle Weigel. I'm professor here, been here since 2006, so only a little bit less than Dr. Nelson. My research areas are in web archiving and preservation and social media, and I also teach a couple of the data viz classes, so visualization and information visualization, and those are things that I'm always interested in looking at, thinking about what's the clearest way that we can present the results of our data and the results of our work, and that applies in presentations and papers and is applicable everywhere.
All right, excellent. Thank you. Dr. Porstar, I know that you have to run to some other meetings. Are you here now?
Yes. Hi, everyone. Thank you so much for this gathering and the Research Expo for 2024. I'm a research assistant professor at ODU and related to School of Data Science. I work at VMask, Virginia Modeling and Simulation and Analysis Center. My area of interest are in definitely data science, machine learning, natural language processing, social computing, web archive. So main goal for me is that I try to connect people to information. We are using large data sets, and these data sets could be different types. So multimodal data sets are focused, and also using algorithms and systems that are trustworthy and resilient. So recently, with the kind of increasing and trending of large language model, I've investigated large language models and also AI conversational systems. And also I have focused on finding patterns and offering counter algorithms to identify deceptive information in online platforms, and specifically on marketplaces, online marketplaces, or other social networks. Thank you so much.
All right, excellent. Thank you. Dr. Jayarathna, our newest tenured member of the group. And a reminder, we will be celebrating his tenure at 3:30 at Hanks. That's on Colley Avenue. And he said he's buying, so...
All right. So I'm Sampath Jayarathna. Thank you all. So I appreciate that. So I joined in 2018, so about 6 years right now at ODU. I was at Cal Poly Pomona for a couple of years. So reset my tenure at Clark over there. From my move from there to here, I reset my Clark and restart everything. So I'm glad that everything worked out. So I'm excited, what comes next. my area of research is in human-computer interaction, applied machine learning, focusing on sensory data, eye tracking, EEG, and all the other various sensors. So our lab's expertise in this particular area, where we are looking at from human-computer interaction and getting sensory data, applying it in various other scenarios. And we are more recently, we are focusing on drone. We are focusing on virtual and augmented realities, and Yassi is going to be talking about some of our applications on this area that we are focusing on, and we're trying to kind of explore a little bit more. And I primarily teach data science related topics, intro to data science. It's always full, so I'll be teaching that in the next fall. If you're interested in, try to get into that soon, because we have quite a bit of new students coming in for the data science, for the School of Data Science. And so that's another role that I play as the graduate program director for the School of Data Science. So I'm excited and happy to see a lot of your faces. Thank you.
Well, unlike Dr. Jayarathne, I'm happy to see all of your faces, not just some of them. Let's see, Dr. Wu.
Hello, everyone. My name is Jian Wu. As you know, I'm still an assistant professor. Hopefully next year I will join the tenure professor club. I joined ODU in 2018. So this is my 6th year. Before coming to ODU, I stayed 14 years at Penn State. I graduated with a very different degree in the field in astronomy and astrophysics. I still love that, but now I'm also love computer science. So my research interests are natural language processing and understanding scholarly big data, information retrieval, digital libraries, and the science of science. So my research has been supported by National Science Foundation, DARPA, and the DoD, and some state grant. So I joined the Web Science Digital Library group when I joined the computer science. I'm very lucky to have Dr. Michael Nelson, Dr. Weigel, and all sorts of faculty working together. And we've been getting along very well, and we're very glad to have my students contribute to this Expo and hear what other students are talking about. Thank you.
All right, excellent. Thank you. Dr. Schock said he'd be a little bit late. And I know I don't have it this way on the agenda, but we have a lot of alumni here. So we'll get a brief introduction to them. And we'll start with Dr. Martin Klein, who's calling in all the way from Paris at the Web Archiving Conference. We appreciate you taking your Friday evening off to join us.
Absolutely happy to be here, as long as you keep organizing those things. It's the easy part is to show up. So appreciate you inviting me being here. Martin Klein, I got my PhD with Dr. Nelson together in 2011, I think. Postdoc at LANL, scientist at LANL, about to... There you go. And yeah, currently in Paris, France for Web Archiving Conference. And since it's 6 o'clock here, I don't know if that's proper or not, but it's happy hour here. So cheers to that. Thanks for having me. Appreciate it.
All right, excellent. Let me see, Dr. Sean Jones.
Hi, everyone. My name is Sean Jones. I've worked with Martin for many, many years. I'm also one of Dr. Nelson and Dr. Weigel's students, and I graduated in 2021 with my PhD in computer science. Now I'm working on the artificial intelligence team as part of the information sciences team at Los Alamos, and I'm learning all about how to be a staff scientist. So you can make it through the process. If you have any questions,
I thought you are.
email me. What's that?
I thought you are now. You're not
staff scientist?
Yeah.
Yeah. I finally got through the process and have been hired as a staff member. So now I'm trying to look at how do I have my own students.
Ooh.
Excellent. Well, again, if you want an internship at Lannel, you know, shoot Sean a message here. All right, let's see, Dr. Matt Kelly.
Hi, I'm Matt Kelly. I'm a WSDL grad from 2019. I am currently an assistant professor at Drexel University in Philadelphia. My original research topic was on private and personal web archiving, so some of you might be familiar with some of that area. I'm kind of continuing on that a little bit and expanding it out here at Drexel for a while. So I'm an assistant professor still, so my tenure, I should be on for tenure in about 2.5 years now.
All right, excellent. And I think our last alumni is Dr. Alexander Nwala.
Hello, everyone. Very happy to see everyone's face here. My name is Alexander Nwala. I'm an assistant professor of data science at William and Mary, and I graduated from ODU, and Dr. Nelson and Dr. Weigel were my supervisors. And my research interest overlaps a lot with the group. But I focus, these days I'm studying various forms of manipulation in social media, and also studying the United States from the point of view of local news sources. Happy to be here.
All right, excellent. Thank you. And looks like Dr. Saoud Alam just joined us, also dialing in from Paris, France. Saoud, are you there?
Yes. Am I audible?
Yes, we hear you. Got you.
And I might have a very choppy network right now because I'm just exiting from the BNF building, the National Library of France. It's a huge building. We just wrapped things up, and I'm just heading over to the hotel. So I'll perhaps join again in like half an hour or something for a more thorough attendance, if possible. But that's the situation right now. I don't know if my background is visible.
Yes. I hope someone's getting a screen grab of that, because that's excellent.
Yeah, so it's like, oh, by the way, you can see Chris, Michael.
Yes. Oh, hey, how you doing?
He's saying,
Hello?
how are you doing? Oh, I have my mic in my ear, so he can't hear you. Sorry about that.
Okay.
Yeah, sorry. Yeah. Yeah.
All right,
Anyways,
excellent.
yeah, but it's wrapped up. So those who are wondering what's going on, I was at the IPC General Assembly and Web Archiving Conference.
Looks like we're losing Saoud. So he said he'd join us again in a second. So with that, we're just about on time. We'll start with our first presentation, and that is Jim Ecker, who is in our group, but is also full-time at NASA Langley Research Center in Hampton, Virginia. And I will stop my sharing. And Jim, you should be able to share the screen. Got it.
Sorry, I have to unmute myself. Hey, yeah, so yeah, I'm Jim Ecker. Yeah, I work full-time. Oh, let me get on camera here. Sorry. There I
Also,
am.
put your slides in slideshow mode, please.
Yeah, I just haven't done that yet. I don't want to share it on that one. There we go. Okay, sorry. Okay, now I'm ready. Yeah, so Jim Ecker, like Dr. Nelson said, I'm a PhD student in the WSDL group, but I also work full-time as a research computer scientist at NASA Langley. And also, before I came to NASA, I did kind of the opposite of what many people did. I came here from Los Alamos. So I worked at Los Alamos in the intelligence and space research group and the space data and software systems branch there, and moved over here. It was pretty cool that so many Los Alamos people are still around. That's nice to hear. As you can see, I'm supervised by Dr. Melson. Tell you a little bit about this is my NASA funded research that I've been doing. This is an AI
Slideshow
system.
mode, please.
It's in slideshow mode. Oh,
Not really.
So it says your screen sharing is paused, and I'm clicking resume, and nothing's happening. I mean, Let me try again. Okay,
you're good.
do you see it now? Okay,
Yep.
sorry about that. Little hiccup. Oh yeah, so okay, so this is NASA funded research on an AI system I'm working on to help with the transformation initiative at NASA for capturing information that's usually lost for institutional knowledge capture, stuff like that. And all right, so here we go. So we're going to be focusing on using this system to capture slideshows, information from slideshows. And as you know, slide decks, presentations, they tend to have a lot of information that is either really dense in a wall of text like you're seeing here on the left. This is a slide from an Army presentation that was given on IEDs and combat behavior. On the right there, that's a NASA slide, and I did not cut that off. That's how the slide actually looks. But it's full of dense information that's structured in a table versus the natural text that you see on the left. But you know, there's also slides that typically lean on primarily images to convey the message, and you know, for the presenter to be speaking to. So on the left there, that's a slide from one of my Scrum updates on some stuff I was working on with world models. Those have moving images, and to the viewer, you can see that one of the models or the architectures controls that little car much better than only one of the models put together. So the one on the right is two models put together. On the right is a one that just kind of relies on the text of the title itself, and then the progression of images to convey the context of what they're trying to say. That's a project. You know, they're talking about going from using the space shuttle over to the SLS, the Space Launch System. That is the new rocket that we've been building at NASA. So for my first research question, I say, can we reliably reconstruct a presentation from sparse information? Okay. So the idea here is if you have a presentation of a slide deck of a presentation with either really dense information or sparse information, could we reliably reconstruct what was maybe said during the presentation just from the slides? And so this is a popular problem. People have made a whole game of it called PowerPoint karaoke. I'm not going to get into it too much, but basically you have a bunch of random slides and you hand them out to people, and then they have to present what's in the slides, and you get to decide who does the best job, just like, you know, a surrogate of the songs in karaoke. Okay, so NASA has a where we disseminate all of our technical communications. This is a system called the NASA Technical Report Server. And when you go there, you can find slide decks from presentations that happen at NASA, but they typically are deliverables, final deliverables for projects. So on the left, you can see it's a final report that kind of condenses everything that happened in an entire series of meetings on knowledge gaps and planetary protection for crewed systems, right? And on the right, that's you'll be seeing that a lot in this presentation. That's a presentation from my presentation at SciTech. It's a conference, an AIAA conference, on some work I did with predicting 3D meshes. But of course, there's a lot that happens during a project, right? So on the left here, these are slides from weekly Scrum updates that we have at work. And the top one is showing how I went from simulated data and predicting where parts are and stuff on that to trying to do it in the real world and having the system, the model I trained was having trouble. So we call that sim to real testing. And so you see the problem I was presenting and then some of the research papers I was reading at the time to try to come to a solution. But that progress that happens through the project doesn't necessarily make it to the final report. And we want to try to capture that. We want to try to capture the process of research that's happening at NASA, not just the final results of the research. So to do that, we're going to primarily try to build a thing called a knowledge graph. So a knowledge graph is just a directed labeled graph, and it consists of these nodes that represent different entities, and the edges between those entity nodes are the relationships between them. So you can see on the left, this is a knowledge graph about Albert Einstein. And you can see that he was born in Germany, and then the relationship between him and theoretical physicists that's his occupation, and theory of relativity. He developed that. And then further on through the graph, you can see that theory of relativity is a branch of physics and so forth. Nothing too difficult for computer scientists to figure out. So, but this is a knowledge graph that's built over time based on data that's inputted into it. And as long as you have the relationships between the different entities, you can draw this graph and have an understanding of the knowledge at any given time. And also, what we're going to be doing is pairing this up with large language models. I left the large language model slides out because I figure everyone knows about it. It's the new buzzword that's going around everywhere. So we're going to pair that knowledge graph with we're going to pair the large language model with a knowledge graph in order to bolster its weaknesses. So to do that, we're going to be fine tuning. I've been fine tuning large language models on data from the NTRS, and you can see an example of a presentation and publication pair here. So on the left, there's the title slide from the presentation on harmonic linearized Navier-Stokes equations, blah, blah, blah. This is like CFD stuff, computational fluid dynamics. On the right, you can see the actual paper. So you take the information from the slide deck, use that as your data, use the paper as your, or maybe even parts of the paper as your target, use that in your training data, and then fine tune a foundational model over that data. Okay, so here's a very, very, very high view of the relationships between different models and different parts of the architecture for Alice. So on the left there, you see, this is the presentation, this is the slide deck, this is the data I want to submit to the large language model. This is kind of the large language model prompt. The large language model then needs to extract and expand data just using the information that's in those slides, submit that to a database, but also use it to help build out the knowledge graph. The knowledge graph then in turn, as you're building the knowledge graph, is able to be used by the large language model in order to check itself, kind of do retrieval augmented generation in a sense, but not against the internet or not against the search engine, but against its own knowledge graph. And that will help with, hopefully it'll help with what large language models do called hallucination, where they just make up data. In turn, the knowledge graph kind of saves itself to the database. All this stuff is kind of held in the database, and then we can create, a web app that interacts with the database to explore everything. So here's an example of extractive summarization from the slide deck. So on the left there, and later on, when you look at the slides, you can click on that link and see a archived version of my gist that I put in the GitHub gist. So you can see all the extracted text. But I'm extracting the text in this way where it's just grabbing all the text that's on a slide, putting it together, labeling it, which slide it's in. And you can see, like on slide 2, the title is Computer Vision During In-Space Assembly. And then I have a section called Difficulties, and we talk about illumination, angle, orientation, movement, constraints, energy, and mass. But on the right, it takes all this kind of unstructured, sparse information text and generates a summary. And, kind of an abstract. And so you can see that it says this presentation, you can kind of read through it. And it does pretty well. I need a way to really measure this. So we'll talk about that in a little bit in another research question. But qualitatively speaking, it does a really good job on doing that. Then another kind of experiment with it was to try to expand that summarization and have the large language model inject information into the summarization that isn't necessarily in the text from the slide. So kind of, and I'm going to use air quotes here, use the large language model's knowledge of what things are being talked about, the entities in there, and inject stuff. So you can see the highlighted version here. I don't ever talk about transfer learning in the slides, but it decided to talk about that on its own. And again, I'm using knowledge in a very, very, very loose sense. It's not really knowledge, it's, you know, math that does it, but it's cool that it kind of expands on that, and it does more than that. So again, you can click on the link there for the gist. Furthermore, we can do it with images. So here's an image from one of the slides, and this is some of the work that was going on where I was, you know, half of the project was just being able to see different parts in orbit and figure out which part is what. And then I have it describe what's going on in the image, and it says it's a very verbose description, but it does a really good job on describing what's going on based on the context that is seen from that original sparse extracted text. So here's the research question. How do we verify the generative extractive information? So this is a really hot topic in large language models. There are various metrics that can be used against the generative summarizations, and be looking into that in the near future. Okay, so this is for generating knowledge graph entries, excuse me, using JSON LD markup. So you can train the large language model to do this. So you can just prompt it to say, you know, generate JSON LD markup for all the entities and relations that are going on in this presentation. So this is the very beginning of it. You can see what's going on. I know you have to do stuff like named entity recognition, entity typing, linking. Really important part is co-reference resolution. So if multiple things are talking about the same reference, the same entity, you have to kind of combine those entity like instances into one entity and collapse everything together, and then actually be able to extract the relations between the entities in order to build it out. But eventually you should be able to build out something like this. This is a part of the knowledge graph that would be built out based on just what you're seeing on the screen right now. So you can see that I presented a talk on synthetic data generation, blah, 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 at the SciTech forum, which is sponsored by AI.play, right? That's kind of the idea. And then I think an even cooler thing, because I love computer vision stuff, is generating it from an image. So if you can do object detection in the image, understand what those objects are, and then figure out the context of what's going on between them, you can build out a part of the knowledge graph just for this image. So you see that it sees a woman and they're feeding a cow, and the cow is eating grass, the woman's holding the grass, and the woman is wearing a mask, right? And as you do that, you can just build out these knowledge graphs, and of maybe you could create a knowledge graph of a movie, right? And just you can see how you could go by different frames and build out what's going on in each frame and kind of coalesce that knowledge graph into what happened during that movie. So the next research question is, how do we verify the veracity of these knowledge graph entries? So one of the main problems with large language models is there's research going on now to try to stop this, but without hard-coded guardrails, how do you, one of the main problems that they have is that they tend to believe whatever they're told by the human through the prompt, right? So if you give them a prompt telling them something is untrue, and they accept that and then dump it into a knowledge graph, then we have a corrupted knowledge graph that will be reporting things that just aren't really there, that don't exist, or maybe that aren't real, events that never really happened, stuff like that. And then you have a bad feedback loop with the knowledge graph and the large language model. So we want to try to figure out how do we figure out how to stop that. So in conclusion, so NASA needs a kind of a central repository for research communications, right? So if you think back to where I was talking about those weekly Scrum slides that never quite make it into an archive ever, those things tend to get saved into like a Teams folder or SharePoint. And to kind of illustrate my point, those slides, I had to go digging through external hard drives that I have, because there was a system we used before SharePoint and Teams that I can't even remember the name of, and that's where we were saving them, and you can't find those anymore. So that it's a major problem, because if you want to try to go back and figure out how projects made decisions and everything, we don't really have a centralized way to do that. Another thing is, when you have speakers that come and they have slide decks, routinely you'll ask for the slide deck and they hand it out in email, but it never really gets disseminated on a wider audience, or maybe it gets saved to a Teams folder that only the audience has, and you have to know to go ask who has access to it to get access to it, stuff like that. So again, a central repository for this stuff would be highly useful for capturing this knowledge that's just unarchived. So Alice provides an explorable knowledge graph, right? So the hope is that once the knowledge graph gets built out, you can go to it and say, hey, I'm working on, say, material science for nanostructures. And you can go to that part of the knowledge graph and explore other projects that are doing similar things as you. Find out like if there's people working on it that you could bring into the team, things like that, or just enable communications between those teams. And it's also a test bed for uncertainties in large language models, since we're trying to understand how to stop them from just believing what they're told through the prompts and try to mitigate absorbing misinformation or disinformation. And finally, slide decks. This is a convenient use case, since this is something that NASA needs to capture pretty quickly. But it's not, Alice is not just constrained on it. They can ingest papers, blog posts, and then maybe in the future videos, like I was saying, trying to figure out a way to extract information to build out a knowledge graph on video. And with that, I'm done.
All right, thank you, Jim. Questions for our presenter?
I have a question. As Jim, you're always teaching me stuff, and I really appreciate that. But I lost count of the number of times you said large language model. I'm just curious. Yeah. I'm involved in a project right now where we're applying them in all kinds of different ways. But I've got to ask, you said you didn't want to dive into it during the presentation, but which LLMs are you using? There's like more than 100 now that are out there. Is this something you run locally? Is it just ChatGPT? Is it Claude?
So I'm a regular, I crawl through Hugging Face constantly. Right? Okay. And so, right now I'm really liking to use the Transformers library that Hugging Face put out, where you can just quickly grab the name of the model and download it locally and then use it against your code. So for stuff like the named entity recognition, there's specific large language model models in there for extracting named entities within text. There's stuff for parts of speech tagging, everything like that. So you can really kind of break down all the different parts of more traditional NLP in order to kind of chain all those models together in an end-to-end architecture to try to get everything you need to try to build those knowledge graphs. So that's a roundabout way of saying I'm trying as many models as I can because we're still very early in the research, right? So since this is funded through proposals I put in at work, and I'm slowly getting money, and because it's NASA, because it's the government, things run so slowly. I started like a year and a half ago getting money for a computer, a really pretty beefy computer to run things locally because it's really hard to use cloud resources for NASA data, right? Even if it's NTRS, it's weird how they do that. So like a year and a half ago, I started getting money. I finally built it like a month ago. I finally got everything together and built it. And I put in the initial proposal that I got procurement money from now, my main pot of money. I put that in last March, and I finally got it in February. So it took a little over a year, but now I'm ready to hit the ground running and really doing this stuff. This is kind of the results of relatively small experiments that I've been running locally on. I have a really nice MacBook, but it's a MacBook Pro, right? Mm-hmm. And running those on there locally, or using Colab when I can get away with it, stuff like that. But I got my hands slapped at work for using Colab, so I have to stop that.
Well, I'll let David Colano ask his question about the hardware that's in the chat. But one of the things that I noticed is that with the series MacBooks, if you run the models too much through Hugging Face, sometimes, and maybe this isn't a problem with the M3 because it just came out, but there's a memory leak that exists in PyTorch. So you might want to watch out for that. I'll try not to ask too many other questions, but I would suggest you look at David Pride's work from the Open University that was presented at TPDL 2023 last year. I think he was doing something that we now call RAG, but they didn't have that term yet. So you should probably take a look at that because, from a digital libraries perspective, it's something interesting. David Pride and Peter North. Martin was nice enough to introduce me to these folks. They are awesome. So you should go ahead and take a look at their work and how they're using it in like an information retrieval setting. And I will wait for the paper for my additional questions. So you better write it.
All right, so I'm going to jump in here. Brian, if you have a quick question, we'll do that. Otherwise, we'll move on to Mohan.
Yes, I do have a quick question. Thank you for your presentation. The use case for videos that you listed here on your conclusion slide, what would it take for that to be implemented, for example?
So I'm not completely sure about that right now. Like the way I initially think of it is doing it by capturing batches of frames in the video and figuring out context that's going on between those, that sequence, using that sequence to chain each other together and kind of build out the knowledge graph that way. That's something that's like just kind of, I think I have it written down in a notebook, the idea of it. So I don't really know for sure how that would work right now. But I imagine that with was it OpenAI Sora, that they've been working on similar things. They have to kind of train that model, right? So I'm really interested in when that model comes out to know, at least on a white paper level, what approaches they took to do that. So
right,
it's a great question. Yeah, I'm wondering basically the same thing, and I just kind of thought about how to try to do it, and I'm waiting for that to come out.
Gotcha. Thank you.
So I'm going to jump in and so Jim, if you could unshare your screen, please, and Mohan, if you're ready to go. All right, got it. All right, excellent. Thank you.
Yeah, so my name is Mohan Krishna Sunkara. So today I will be speaking on one of my recent research paper that is detecting deceptive dark pattern web advertisements for blind screen reader users. So when it comes to deceptive ads, visually there are around 2.2 million billion people of vision impairment. 36 million people are affected by being blind. These people use screen readers to navigate around the web, but the thing is, the screen readers, in order to make the screen readers work well with the website, website has to be made accessible. They has to follow certain set of guidelines, which are known as WCAG guidelines. And the question is, not only like whether the website follows it or not, like they has to do something like to increase the usability of it. They has to how easily they are able to use the like the elements in the web pages. The most of the web pages are complex HTML DOMs, and they have absence of textual alternatives for visual components, makes web pages difficult to navigate and read. And blind people are often deceived by the advertisement that seamlessly integrated the web page content. And there are many ad blockers available, but they fail to remove the internal advertisement placed by website itself. Screen readers are, as I just told, there are many types of different types of screen readers. Screen readers basically it narrates the content on the screen and enable navigation via keyboard shortcuts. And screen reader plays a critical role in enabling visually impaired users to interact with the computer applications by providing the visual output. But to remember, in order to use a screen reader, the blind users has to remember various shortcuts. So remembering these various shortcuts for different screen readers can be challenging for the users, because like if the one user mastered with the one screen reader, in order to use another screen reader, they have to again learn. Sometimes it can be confusing for the blind user to use different set of shortcuts. And when it comes to dark patterns refers to the deceptive user interface deceptive user interface design that manipulates user in behavior, often leading to the unintended actions such as purchases or signups. These patterns has become prevalent across various digital platforms, leveraging cognitive bias and hiding essential information to deceive users. There has been a lot of work done on these dark patterns extensively, but there has been relatively less focus on deceptive online ads. And this lacks visual context. This lack of visual context increases the risk of blind users in like not knowingly interacting with the advertisement. For example, if the blind user is using the website, the screen reader automatically reads that the web element is the advertisement to the blind user. Suppose if the web element is not like tagged that it is a advertisement, then it is not the blind user will not know that it is advertisement, and he is forced to go on that particular web element. This is called deceptiveness. For example, many of the websites has advertisement, but they use a particular tag called ARIA label in order to tell that is advertisement. But what some of the website does is, as you can see in the image, they make sure the web element is a part of the web page, but by not tagging it with the ARIA label, so the blind user doesn't know it is advertisement. So if by mistake, if he clicks on those web element, it will take him to a different web page, or it will open up a pop-up. By doing that, blind user again has to refresh it or come back to the original page. So this will actually create a lot of struggle for the blind user. And there has been a lot of efforts done in order to stop these ads. There have been a lot of apps like ad blocker and ad guard kind of, but the websites, these apps actually block the communications from the ad servers to the web pages. But the thing is, when the there are few websites which will stop, which will lose heavy part of revenue by using this ad blockers there. So the many websites are trying to use some techniques to detect whether the user is using the ad blocker or not, and they are trying to trying to stop the an access to the website unless and until you stop using the ad blocker. So there has been a lot of research done on this, but when it comes to blind user, how to give him proper information that say this is a particular type of ad or not, that type of research has been not done. So for knowing the in-depth details or in-depth problems the blind people face with the ads, we have conducted an interview study with 18 blind people. The age of the blind people ranges from 22 to 66, and they were all familiar with the screen reader and browser experience. They are all good in the web browsing experience. They're all proficient in English, and we have excluded the children of below 18. And we have conducted semi-structured interviews via Zoom, via Zoom call and all. And we have provided them with the contest and recorded the session. And then we have analyzed the data using open and actual coding techniques. And these are the demographics of the blind people. So this, a few of them uses JAWS, few of them uses VoiceOver. VoiceOver is a different screen reader for the Mac. The few of them uses JAWS, few of them uses NVDA. These are different types of blind users. So what we found from the interview study is many of the blind users avoid using ad blockers due to installation and configuration difficulties. And also using these ads, the disadvantage of ads is this will prolong the web activities for the blind user due to screen readers, linear navigation, and making the navigation tedious. And also most of the common types of ads include e-commerce, these memberships and native promotions, and etc. So when the blind user accidentally click on the this ad, it will take them to the different like page or open up a pop-up. So these ads are strategically placed at the middle of the content so that the blind user thinks that it's a part of content and clicks on the ad. And one more thing is most of these deceptive ads are not cautioned, and also they are not tagged with their area label or any other tags, so that blind user are easily disabled with these ads. And in order to find out automatically these ads, we have developed an algorithm. So the algorithm first traverses all down and then checks whether the and then gets all the elements from the particular node, div, iframe, or script, a tag, image, or this few nodes, and then it will go through each child nodes, and it will get all the nodes. And each node, each web element node, is we extract the particular set of features from it. For example, textual features, the surrounding text, or the image. If the ad contains an image, we get the image from the ad, and we get the surrounding information. And we also have our own handcrafted features. We get that information from that candidate element, and then we pass that candidate element to the multimodal classifier which we have developed. Once we pass it to the multimodal classifier, it will make prediction. And then once the prediction is made, depending on the threshold, we will classify whether the web element is ad or not. So this is the classifier which we are working through. So first we'll go through a website, and then from the website we first extract all the web elements. From each web element we get the ad, the text inside the ad, we get that information, and we send it to the transformers for getting a futures of it. And then we get the image information, image, that ad information, the image in the ad, and then we send it to the vision transformer to get again the image embedding. And then we get a set of handcrafted features, which I'll discuss in the next slide. And then we send all this to the multimodal classifier. The classifier has a various encoders and LSTM layers, and the encoders are basically we extracted from the transformers, which are multi-head self-attention encoders. And it also has LSTMs, so it also has a final dense classifier layer at the end, so that will classify whether the ad is deceptive or not. So these are the handcrafted features we have actually through experiments we have came up with this handcrafted features. The first handcrafted features is web page summary. This extracts the summary of the web page, and next is context similarity. How much the ad text and the web page summary, how much they are similar. Many of the time, the ad text and the web page are completely different most of the time. And whether the ad has the area label or not, we also see it. We also get the information about that. And the readability score of the ad, many of the time we found out that ad text ranging, they have very less readability score. And also the URL which the ad is redirecting, the web element is redirecting, whether it is secure or not. Most of the time, the deceptive ads, they don't have the secure tag, the HTTPS tag it doesn't have. And also whether the URL has IP before address or not, we will check. Most of them they will not have. And also the URL is short-lived, or it is active or inactive. Most of the time it is not active, because they deceptive ads take only temporary URLs. And also one of the common pattern we observed is whenever a user clicks on deceptive ad, it will generate multiple redirections. This is also one of the nature that is also we consider while we extract information from the ad. And we have constructed for training our model, we have constructed a data set. We have from 500 different web pages, from diverse domains like travel, news, blogs, and e-commerce. We have collected the data, data. First we'll go to for annotating the data set. First we go inside the data, web element and then website, and then we see if the ad is we annotate ad. We add our custom attribute, data attribute, such as data deceptive. We add this attribute, and then we annotate this attribute true or false, depending on the ad is deceptive or not. If the deceptive, we add a custom attribute data deceptive as true. If it is not deceptive, we will add it as false. And then we use this annotated web page in training, like we have collected 1200 samples of these data, like data web page, annotated web pages, and then we have created supervised data set, and then we have trained it. And these are the hardware, for the hardware things which we used for the training. We have used NVIDIA V100 GPU with 128 GB memory per node for training, and also we have used Adam optimizer. We have conducted over 25 epochs with 0.1 validation split, and then we have used reduced LR on plateau and early stopping to optimize the training. And then when we have conducted the evaluation, we have observed that when we consider the model with the ResNet 50 plus BERT without any futures, the model accuracy is 0.66. And then when we compare, when we look into the proposed model with the futures, the model precision is 0.85. When we consider precision recall FN score accuracy, the model accuracy, like model precision recall FN score accuracy, has increased up to 30%. When we consider all the futures along with our proposed model. And we have also conducted ablation study to see the performance of the hand-crafted futures. And when we compare the baseline model, the precision is around 0.70. It went up to 0.865 when we taken all the hand-crafted futures. And one more thing, when it comes to limitations, our model has actually trained on only English language web pages, and also small number of small number of web pages. So we plan to, in future studies, we plan to increase the number of data set size, and also number of dark patterns, number of the annotated web pages which covers remaining dark patterns as well. For example, there are other types of dark patterns such as Roach model, Jukering. Roach model is Roach model is one of the another dark pattern in which user once he sign up for anything, any purchase or something, he is unable to sign it unsubscribe. For example, if the user buys some subscription plan, the Roach model type of deceptive thing is there is no unsubscribe option. So it's like the model which you cannot come out of it. So there are different types of dark patterns, and also bait and trick is a bait and switch. Bait and switch is another type of dark, deceptive thing. In that case, in which the user is presented with certain set of products and with a very low price, and when the user go inside that website and when user start getting engaged with that product, then the price is suddenly increased. This is also another block, dark pattern. So in order to evaluate all the set of dark patterns, we need to increase the data set size, and also we need to come up with a different model. So we will be exploring that in the future research. Another, as I told you, we need to increase the annotated data set size for the new dark patterns, and also we need to use different we are trying to use different set of deep neural architecture and also different pre-trained models to increase the accuracy of it. And also in order to use this algorithm, we are planning to develop a Chrome extension. The Chrome extension basically will detect a deceptive ad, and then will generate alternate tests, and will be presented for the screen reader in order to present it for the blind user, so that blind user will come to know whether the ad is deceptive or not. So we are trying to build a browser extension, other systems which has these capabilities. And also this is the we are more in order to have informed interactions for the blind screen reader users, we are coming up with even more, we are trying to find it out. We are trying to find out what are the other types of informed decisions we can give it to the blind user, so that they will be well informed before doing any certain task, or which will increase the trust in them while for using the web interfaces. So in a summary, we have actually explored the deceptive content of the blind screen reader users. We have, for exploring in depth, we have conducted a interview study that has 18 blind screen reader users that has revealed that they are having a very difficulty in using a website which has a lot of deceptive ads, which will consume a lot of their time and which will increase their effort. And also for reducing that, we have developed an algorithm. That algorithm basically has achieved F1 score of 0.86 on a representative data set and 0.88 on in the wild evaluation data, in a wild evaluation. In the wild evaluation means we have tested our model on the data which is not seen. So in that case, we have got 0.88 as the evaluation. And also, as a part of future research, we are trying to explore other kind of dark patterns and then trying to develop the models which will detect that kind of dark pattern. Yeah. So thank you for. If you have any questions, please.
All right, questions for Mohan. Thank you, Mohan.
Yeah.
Hi, Mohan. Can you hear me?
Yeah, I can hear you, please.
Okay, awesome. Thank you for your presentation. Hopefully it's not too loud for the background, but my question is specifically the ablation study that you did. What was the purpose of that?
Oh yeah, so the ablation study is like this is a baseline. So the baseline has not considered any of the hand pepper features, and when we add each hand pepper features, how it is affecting the precision recall. In order to capture that information, we have done this ablation study. For one, I will show this thing. Yeah, you can see this algorithm workflow. In this algorithm workflow, there has a third part. We are considering these the hand pepper futures. So the baseline doesn't have these hand pepper futures, and then as we move ahead, we will add each of the futures has hand pepper futures. So we are trying to see how it is impacting the model performance.
Gotcha. Thank you.
Yeah. No problem.
Other questions for Mohan? So I have one question.
Yeah.
In classifying something as deceptive or not, what is worse, a false positive or a false negative?
I think false positive can be worse, because if we are saying something like if it is something has a deceptive which is false positive, if we are saying something has not deceptive, when it's actually deceptive is actually more dangerous, because we are blind screen reader users will click on that and again it will redirect into some different page and will open pop-up, then he has to go again start from the he has to hit a refresh or close the browser, or else even if you do anything he has to start again from the top. So it will waste their at least 5 to 10 minutes of the time, depending on where they are on the web page.
Okay, thank you. So so in the evaluation, you have precision, recall, F1, etc.
Yeah.
So one of the aspects is there's actually nothing special about F1. It's the one we all use, but there's actually F05 and F2 and whatever, right? So you can balance precision and recall. And if it's clear that a false positive is worse than a false negative, maybe you could also report another F score.
Okay, sure.
And I can never remember, if you make the number smaller or bigger, which one you're weighting. I always have to look that up. But there are other scores defined than just F1. So.
Oh yeah. Yeah, we'll make sure that we'll cover this next next extended version of it.
All right. With that, we'll try and stay on schedule. Thank you, Mohan. And let me see. Next up, I believe we have Xin.
Hello, Professor Nelson. Let me share my screen.
Okay. Got it?
Yes, it's working.
Yep. Thank you.
Hello, everyone. Today I will be talking about our paper, Visual Descriptor Extraction from Patent Figure Captions, a case study of data efficiency between BiLSTM and Transformer. The number of patents in the United States has been steadily increasing in recent years. As shown in the image below, particularly in 2020, we have a large volume patent grants. It's 388,000 patents, among which 34,000 were design patents. On average, for each design patent, there are 8 patent figures. So each year, we face a large volume of design patent figures, and we would like to know about them as much as possible. This is the focus of this paper. What we actually do is to extract textual descriptors for technical drawings in design patents. It can be subsequently used to build search systems. Researchers and patent examiners can use this research system to search for technical drawings based on their needs. It can also be used to build a large-scale data set and for computer vision purposes. Let's look closer at a patent. It includes an XML file and a number of figure files. On the left-hand side is the patent file. The format of it brings convenience to us to extract information and put it into a structured data set. We can obtain metadata such as patent ID, patent date, as well as abstract main text. Figure captions are also included in main text references. It also provides figure properties information such as width, height, and orientation, and so on. On the right-hand side is the view of the patent figure files. Those patent figures belongs to one patent, so it's a number of patent figures associated with the patent file on the left-hand side. In general, there are 2 major categories of patents: invention patent and design patent. Invention patent is more about a device or process which delivers a new technical solution. And this kind of patent usually has no main text. Below is an example of it. And from this figure, it's not easy to figure out what it is. And the second category is design patent. It's more about appearance, and it has very short main text, and usually it only contains figure captions. And in this paper, we only look at design patents. So this is what we generally look at in a patent figure. On the left-hand side is the patent figure. On the right-hand side is the figure caption and the useful information we can generate from it. Patent figure name, object in it, and the aspect of it. One thing need to be mentioned here. So we can see the figure name in the figure file. It's figure 1, but it's not provided in any textual format in the figure file. So in order to associate it with the information we have, we need to use some OCR tools to extract this figure name. So here, maybe it's easy to figure out what the task of our research. It's similar to what people do in the annotation of ImageNet. So in ImageNet, it's human annotation for a large number of figures, and they give a class the figures such as cat, dogs, and cars. We do something similar here, but there are also differences. When we do for pattern figures, we do not use human annotation, but we use NLP methods. The second difference is that we don't look at it's not natural images as in ImageNet. It's technical drawings. In the image, we have dots and strokes, and it's generally black and white. There's no other color. And another important part for the technical drawing identification is the perspective classification. We need to figure out whether it's front view, end view, left view, right view, and so on. There are many other aspect classes. So actually, we do the two things at the same time. We need to identify the object in the figure and do perspective classification. There is the pipeline of our work. We start from the XML file. We pass this file and obtain metadata and figure captions, and then put them into the SQL database. Now we randomly select 3,300 figure captions from the whole dataset, and manually allocate them to obtain the ground truth, and then use the ground truth data to do training to obtain the NLP model. Then we feed the figure captions into the NLP model to obtain the object aspect, and put all of them in the SQL database. On the other hand, for figures, we need to, because there's no textual information about the figure name, so we need to use a text extractor for figures. And here we compared a lot of existing OCR tools, and we choose to use Epson recognition to create the label, to extract the label. And the label can associate the information in the database with the figures. Then this is a complete database for all the figures. Next, I will talk about ground truth data. The method we use here is named entity recognition. Existing ER models is not applicable here, since they can only extract person names, institution names, and locations. It's not what we want. We need objects and aspects. So we need to train our own model. First of all, we need to build our own training, testing, and validation dataset. And we need to annotate them by ourselves. In the image below, it shows how we do the this is a demonstration of the annotation. We annotate per aspect and object, like what's shown in the image. Actually, in practice, we use a BIO schema with 5 tags. This schema will tag each of the words in the sentence. So B aspect means the beginning of aspect. So front will be assigned this tag. I aspect means inside aspect. So perspective will be assigned I aspect. And this is similar for B object and I object. O means outside. So it means words, not aspect, not object, some other words in the sentence. And then after we got the ground truth corpus, we split them into training, testing, and validation datasets. Then we use two architectures to build a model and compare the performance of them. The first model we use is BiLSTM CRF. There are generally 3 layers, major layers. First of all, in here we have the input sentence. A is a front view, and it's feeding to the input embedding. And we use some pre-trained language models such as BERT, Roberta, and so on. And we also use some regular embedding models such as ELMA, trained from recurrent LSTM, and also embedded model trained from Word2Vec. And this embedded model will convert the input sentence into a embedding, and it's fed into the BiLSTM layer. This layer captures contextual dependency for each token and outputs the scores of possible tags for each token. And it goes into the next layer. It will learn the joint relationship between tags and further refines the probability scores for each token. And then we pick the tags with the highest probability. So finally, 2 of the words in the input sentence were assigned meaningful tags, tags. It's B aspect and I aspect. So we got to know front view means aspect in the sentence. And the second model we use is transformer. Transformer is based on the attention mechanisms, and it has a number of encoder and decoders. And it's different from the previous model because it will assign different weights to each token in a sentence. So this mechanism has the ability to focus on a particular part of the sentence. This is why it's called attention mechanism. And here, similarly, we can input the embedding into the model, and it will output the tags with the highest probability, B aspect and I aspect. And we got to know the aspect and objects in a sentence. Next, I will talk about evaluation. Here, the model is BiLSTM and CRF, and here we look at 7 embedding models. The first 5 are embedding models based on self-attention mechanisms, and the other 2 are conventional embedding models. And it's and the output shows that the embedding models of the pre-trained language embedding models has better performance than the conventional embedding models. And among them, Descriptor shows the highest F1 score. So then we do a comparison between BiLSTM CRF and transformer. In general, BiLSTM CRF shows better performance among each of the embedding models. And for BiLSTM CRF, the performance doesn't show significant difference. So it performs well in the general level. For transformer, it's a little different. There are bigger variances in the performance, so it's not as consistent as BiLSTM CIF. So after the comparison, we decided to use BiLSTM CIF as our model to train the data. There are also some discussions. We look at data efficiency. We vary the training data size from 500 to 2,700. And we don't have more training data. It's in this range. And you can also see the 5 curves of BiLSTM and the 3 curves for transformer. And transformer increases significantly, but it's consistently lower than BiLSTM. And we discovered transformer is very sensitive to data size. And this also shows that BiLSTM is better than transformer in the scenario of limited training data. This, to some extent, explains why transformer is not as good as BiLSTM in our tasks. And we also look at generalization. In the training data, we don't have a lot of sentences, and we only have 557 distinct object names and 348 distinct aspect names. Then we use the trained model. We applied it to a larger corpus, which contains 66,000 single figures. And in the output, we have 6,000 distinct object names and 2,000 distinct aspect names. And we compare it with the training data. We found 98% of objects, 93% of aspects extracted are new. So this means when fit something new to our model, it will generate new output. This shows the good generalization power of it. So this is the discussions. And so finally, it's the conclusion section. In this paper, we proposed an effective visual description extractor using the BiLSTM CIF sequence tagging model. And the overall F1 score is 96.6%. We compiled a data set with 3,300 captions, which is human annotated, and this data set is publicly available. We performed a data efficiency study and tried to look deeper into our experimental results and see why BiLSTM CIF is better than transformer in our case. The pipeline discussed here is an important module for a bigger project, which generates the patent too. It's published. This paper is published in last year, and it's a large-scale data set with 2.7 million technical drawings. It's so far the largest large-scale data set for technical drawings. It can be used for scientific figure retrieval, 3D reconstruction, and some other computer vision tasks and so on. So this is about the this is about our paper, and this is my presentation. Thank you for listening.
All right, great. Thank you, Xin. Questions for Xin?
I have one question. Jean, thank you for your presentation. The models that you presented and basically described their purposes, what was like the relationship that helped you to make the decision to use those two models in your architecture design?
Okay, so are you asking why do I choose the two models, but I don't use other models? Is that
yes, exactly. Yeah, exactly.
This is a good question. So the reason why I choose BiLSTM CIF is that we want to the method we choose to use is named entity recognition. And typically it's used to extract person names, institution names, and locations. And it's also, as shown here, it can do our tasks. And the most widely used method for this, a model for this method is BiLSTM CIF. So it's natural I choose this model. And for transformer, because it's the newly emergent and very powerful, especially in translation and generating embedding models. So initially we guess it will be more powerful, but the results turns to be not like that. So this is how we choose to use those two models.
Thank you.
Mm-hmm. Thank you.
Got a question. What will be the impact of it? Say it is accurate, it's working great. How big of an impact it will have? Like the problem it's solving, is it not solved by bigger corporations or anything already in some way? Or is it making things more democratized to like making it available to everyone, even with the like least powerful laptops? What's the overall impact of it?
Let me repeat the question. Are you asking about the novelty of this paper and the impact it poses to the academic society? Do you mean that?
Academia or whatever is the community that is impacted with that, right? And also, what is the problem that people are unable to solve, and what this thing will make it easier, right?
Oh, okay, I got it. Thank you. It's a good question. So it's like here we have ImageNet. We have like in ImageNet we have a lot of figures, but we don't know what it is without looking at them. So they hire people to do annotation. They give a person a figure and they will assign it's a cat. Another figure they will assign a dog to it. This is, and they have did this by human for really a large number of figures. What we want to do here is similar. Actually, we are doing a computer vision thing. We are preparing a benchmark data set for computer vision. For example, this is a technical drawing. There is a shirt in it, but a jacket, but we don't know what it is without annotation. We need to annotate each figure in this data set.
So I got that. I followed up with.
But there is no.
But I was the problem that you're trying to solve. I'm saying if I were to upload this image to say ChatGPT or something like that, and ask it, will it not be able to describe the way your system is describing it?
Just to chime in, so this work was done 2021, 2022. The paper was published in 2022, I believe. So at that time, we were not considering using any large language models. Our language model was just been popular over the past 1 or 2 years. So, and this work was part of the bigger pipeline that's we used to build DeepPattern 2. So because we needed to build a large data set which have all the technical drawings annotated. So that's why we need to get this object and aspect extracted exactly as they're shown here, instead of just showing the captions. So, right, the scope of this work is a little bit narrow to this pattern captions, but you know, another impact is that another demonstration to show that in the NER tasks, the BiLSTM actually it beat the transformer model, and there are other, and the result is consistent with other studies.
I would like to add. I also would like to add some more sentences. Yes.
Yeah, I think we're running out of time. If you for any other questions, I think we can discuss offline.
Just 2 sentences. Here it's technical drawing, and we don't have much experience in computer vision with technical drawing. We only have experiences with, existing in the existing methods. There's only about natural images, and that is based on the color pixels. So I doubt whether large language models can work this out, because in this world, there's no much experience about technical drawings. So they may do well for for natural images, but I doubt whether they can do well for technical drawings.
Right.
Yeah. Thank you.
Okay. With that, thank you, Jen. And let's see. Next up, we'll have Tarannum.
Okay, so is the screen visible?
I have it. Yep.
Okay.
Got it. Thank you.
Okay. Thank you. Hello, everyone. I am Tarannum Zaki, and I'm a PhD student in the Department of Computer Science at ODU. I started my PhD in spring 22 under the supervision of Dr. Nelson and Dr. Weigel. So today I'm presenting our research regarding misinformation and disinformation spread on social media, titled Web Archives for Verifying Attribution in Twitter Screenshots. So social media has become a common way of sharing information these days. And some of the popular social media that we all are familiar with are Facebook, Twitter, Instagram, etc. And people are constantly sharing their thoughts and ideas on these platforms all over the world. So though there are ways to interact with posts on different social media platforms, such as share, like, react, comment, and so on, screenshot has now become a widely used means of user engagement recently. So people are often annotating content posted by social media users, for example, fabricating it in some manner and then making it viral all over social media. So here we can see some examples of posts where certain tweets, reply thread, quote tweet are shared as screenshot on Twitter. Now, why people think of using screenshots to share content despite of having different ways to interact with the post? So one of the reasons is to use as evidence for deleted posts, because there are chances that controversial posts might get deleted. So we can see here an example where a user shared screenshot of another tweet regarding the Uvalde shooting incident. So if you try to find it on the live web, you'll see that the post doesn't exist anymore. However, it is found to be archived, which indicates that the post might have been deleted at some point. Other reasons people use screenshots that they want to aggregate multiple content or try to annotate it in some manner. And one of the vital reasons is to use it for cross-platform engagement. So by cross-platform engagement, if I say, so there are no internal mechanism to share a post of Twitter on Facebook. So what people do is they use the screenshot of a tweet and then post it on Facebook. And this way they perform a cross-platform engagement and utilize screenshots. Now, if we search social media, we can see tons of screenshot examples floating around. Some might be purposed as satire or humor, such as one of the examples you can see here is of Elon Musk's fabricated post when he took over Twitter last year. Other examples involve spreading different types of disinformation or misinformation. But whatever the purpose might be, users rarely verify before sharing whether the content of the screenshot was really posted by the alleged author. So this might mislead users and eventually cause the spread of misinformation and disinformation. Now, fake tweets are relatively easier to create. There are different online tools available. Here we can see an online tool, TweetGen, which is used to create fake tweets. So this tool basically provides an interface of editable attributes which can be easily formatted to create a fake tweet. But there are ways where we can validate the attribution of screenshots. So we can use the live web, we can use the Google search, there are fact-checking websites, we can use the web archives to validate whether the content of the screenshot was actually posted by the alleged author or not. So what motivates our research is that we see that fake tweets can be responsible for misinformation and disinformation spread. We saw that fake tweets are easy to create using online tools, and there are no tools currently available to evaluate the authenticity of the attribution of screenshots. So the aim of our research is to develop a tool that would automatically provide a probability whether a screenshot of a social media post was actually posted by the alleged author using the services of live web and web archives. So today I'll be discussing the web archives part, how we can utilize the service of it to validate the attribution of screenshots. So how typically a web archive works when we want to search whether a particular post, in this case a tweet, exists or not. So if we have a URL of a tweet, we can simply just type it in the search bar, the Wayback Machine, and we can see if it's archived or not. But in case of screenshots, most cases, URL of a tweet is not present in the screenshots. So how can we utilize the information that exists on the screenshot to find it in the web archive? So we have the Twitter handle and we have the timestamp. So what we can do is we can see the construction of the tweet URL here, and the tweet ID basically encodes the timestamp of when the tweet was actually created. So we can use the Twitter handle and approximate a time window based on the timestamp we have on the screenshot, and we can construct the URL of the tweet and then further search for the tweet in the Wayback Machine using the URL. So this is the basic idea how we want to validate whether the content of a screenshot actually exists in the web archive or not. So here's the entire framework, how we are using the process to verify if screenshot exists in the Wayback Machine. I'm not going in details here. I'll be discussing the basic steps in the upcoming slides. So we are working with screenshot images. So we need a data set, and we have created a data set of screenshots that we collected from Twitter. So far, we have collected around 200 examples, which include both real and fake screenshots. The data set description is detailed in our blog post. So we are collecting the screenshot images and the fields that we are describing for a particular data is we are collecting the shared posts URL, the original posts URL, the category, whether it's real or fake, the reason, how manually we are attributing it, whether we find it on the live web, through Twitter advanced search, or by using the web archive, and the content category, whether it belongs to politics, entertainment, and such, what type of post it is. Is it a tweet, a quote tweet, or a reply thread? The structural features for single tweet, it would have a single author and single post. For reply thread, it might have multiple author, multiple post. The search strategy, and we have started working with the Twitter, so we are also mentioning the social media. The next step is to extract the important information from the screenshot. So we are performing the optical character recognition, which extracts information as text from the digital image. So we have established methods to extract the Twitter handle, the tweet text, and the timestamp from the OCR extracted output, which is detailed in our tech report and which I also presented in previous year's student capstone conference at VMask. The next step is we are computing a time window based on the screenshot timestamp. So we extracted the Twitter handle, we have the screenshot timestamp, and we are computing the 26 hours before the screenshot timestamp and the 26 hours after the timestamp. So we are actually considering this time window of 26 hours because to deal with the time zone discrepancy. So someone who is tweeting and someone who is taking the screenshot of the tweet might be in different time zones. So to deal with that, we are, and because when we take a screenshot, when anyone takes a screenshot, the timestamp is basically the one that the time zone he is actually in. So to deal with this time zone discrepancy, we are considering a time maximum time difference between the two time zones, which is 26 hours. Next, we do a CDX API prefix search to retrieve the archived tweets with the left-hand boundary. So with the left-hand boundary, we can get the archived, we can retrieve the archived tweets. And when you use only the left-hand boundary, because a tweet can be even archived today. So that's why we are retrieving the archived tweets with the left-hand boundary, and the right-hand boundary is the current timestamp. Would be the current timestamp. Next, we extract the tweet IDs and determine the tweet creation timestamp using the tweet-edit tool, which was developed by our Wisdom members. And you can see here the archive tweets URL, where the tweet ID actually encodes its creation timestamp. So we can get the timestamp using this tweet-edit tool. We do a mapping between all the tweet IDs and the tweet creation timestamp. Then we determine the archived tweets by filtering the tweet creation timestamp within a particular time window. So this is basically an optimization process. Here I've given an example that initially within the left-hand boundary, we get, for a particular example, 917 archived tweets. The next step that I showed previously was we do a mapping between the tweet ID and the tweet creation timestamp, and the creation timestamp of the tweets which doesn't fall within the 52 hours. Now we are considering a particular time window, the 26 hours plus minus 26 hours on either side. Those are filtered out. So that reduces us to 449 archived tweets. And we only need a certain tweet or a post can be archived multiple times, but we only need one archive version to prove its evidence. So we can exclude the multiple mementos. We can filter out that. So that reduces us to 29 archived tweets. So we can see here that this optimization process actually helps us to reduce the set of retrieved archived tweets, the initial set of retrieved archived tweets to a much reduced set. The next step is that after we get the retrieved archived tweets, We extract the tweet text from the archive trees using Beautiful Soup and Selenium. We can see that the HTML tag that contains the tweet text, we simply just extract the content of it. And finally, we compute a text similarity score between the tweet text from screenshot and the archive tweets using the Python's difflib library, which basically works that the text similarity score is computed based on the longest common subsequence. So we have the extracted text from the archive tweet, and we have the extracted OCR extracted tweet text from the screenshot. So when we compute the text similarity score, for this example, we can see that we have a text similarity score of 81.40%. And that doesn't match exactly because, as you can see here, that when we extracted the text from the archive tweet, there are some hashtags which, for due to maybe some OCR errors, we didn't get when we extracted from the screenshot image using OCR. So we can get multiple archive text and a lot of match scores. We take the highest match score, and this highest match score actually helps us to prove the existence of the screenshot tweet that was posted by the alleged author. So we performed this experimented on 108 single tweet images that from the dataset that we collected. Here we can see the performance of the overlap between the tweet text from the screenshot and the archive tweets. And we can see that a threshold of 60% produced the highest F1. Regarding the limitations of our work, we just started working with single tweet images, which are a very simple form of screenshots. But the limitation is that these are screenshots, and screenshots are cropped images. People can take screenshots in various forms. So there are different complex screenshot images. There can be reply threads, concatenated images, and even you can see here there are annotated tweets. Another limitation is that when we're using the OCR, we have encountered different examples. When we perform the OCR, it returns different garbage values, which we cannot further utilize to process. So we'll be experimenting with these exceptions in our future work, and finally integrating all the search strategies to automatically, so that we can automatically detect whether the attribution of a screenshot was actually posted by the author or not. So in summary, we can see that screenshots are an easy way to share content on social media, and screenshots can be easily faked, and particularly when content are shared using screenshot, it is a critical task to detect a fabricated posts. Here we have seen how we can use the services of web archives, which could be useful to verify attribution of a screenshot by simply finding an archive version of the screenshot content. And we believe that our research will mitigate misinformation and disinformation spread on social media. And that brings us to the end of my presentation today. Thank you for your time. I appreciate the opportunity to speak about our research today at the WSDL Research Group Expo. And I'm ready to answer any question regarding this topic now.
All right, thank you, Tarannum. Dr. Nelson had to step out for a few minutes, so I'm taking over as host. Does anybody have questions?
I have a few questions. I mean, first off, I wanted to say that this is really cool. Okay, I've sort of wanted something like this sometimes for my personal work, but I did have a few things like. So you have the time window based on the timestamp that's in the tweet itself. That makes sense because some people don't put that in the tweet, but that's another problem. Some people will crop that out of the screenshot.
Yeah.
But assuming you have that, the other thing is you mentioned something about the timestamp of the image. I was kind of confused, and I'm trying to remember. I think it was around slide 14. So are you just using the, and I'm not saying this is a bad idea, I'm just saying, are you just using the timestamp that's inside, the red box there on the left? Or is there some other information you're bringing in as well that you have access to?
No, we are just using the timestamp that we are seeing on the screenshot image. And as we know that, if someone who is tweeting can be in some time zone and another person who is taking the screenshot can be in in another time zone. So to deal with the time zone discrepancies, so we can actually approximate whether this tweet was posted within a certain time window, we are searching this particular tweet within the time frame of 52 hours, like plus minus 26 hours on either side. But we are not using any additional information for the to approximate, you know, the timestamp. We're just using the timestamp of the screenshot image.
Okay, so and why the range? You actually know that when the tweet was tweeted.
Because this is a screenshot, someone actually shared it. If I go to a previous example, maybe this one. So this person tweeted, shared this screenshot. I don't know the time zone when the screenshot was actually the screenshot was actually taken.
I see. So you've got the time zone of the screenshot, and you also have the time, which is a screenshot of a tweet, and then you have the tweet of someone sharing it as well.
Yeah.
That's where I was confused. Okay. Yeah, that makes it far more complex.
Yeah. So
and
just
the other question. Oh, so
yeah, sure. No, you can go ahead.
Oh, the other question I had was difflib, part of the Python library. Now I didn't know this. So I was going to say, why did you choose that over, you know, some other text comparison methods?
So this was chosen. This actually computes based on the longest common subsequence that matches. Okay. So as you can see here, we want to get the match as much as possible, because the limitation with the OCR is that in some cases, due to OCR errors, we don't get some information extracted. So the one we get extracted, we just want as much as possible to match. So that was the reason why we are using the longest common subsequence part. And for that, we are using...
That totally makes sense. So what were you using for OCR?
Oh, so OCR, we started with the PyTesseract, but later we also experiment with the easy OCR, and we decided that if for a particular screenshot image, for some cases, PyTesseract gives us less information, easy OCR is giving us more information. So how we can utilize the both OCRs? So one way we decided was we take the output of both of them and we compare. For example, we get from PyTesseract, we get the tweet something as the Twitter handle. From easy OCR, we get something as the Twitter handle. If both of them matches, we can decide that, okay, this is the Twitter handle we extracted. If it doesn't match, we consider the one that matches. And if both of them gives different results, we proceed with both of them. So that's how we decided. But initially, we started with the PyTesseract one for the OCR.
Yeah, a lot of us do that, and it doesn't go well. No, I like your method, and you might want to, if this logically makes sense. This is just something that came off the top of my head, but I think you can do this comparison because they're tweets and they're small and they're short. But you know, whereas if you're trying to compare huge documents, you wouldn't be able to use this method. But you might want to mention that when you talk about this further.
Oh,
that is really cool. Thank you.
Thank you. Thank you so much.
So Tarannum, if the quality of the OCR or missing some words here and there was an issue, did you try just comparing or counting letters that were recognized in both the cases and just seeing how many times E appeared, how many times J appeared, and so on, and just character level, similarity?
Character level similarity. No, I actually haven't explored with that, but that's actually a good suggestion.
For the small text, that might actually just work.
Yeah. Yeah. Thank you so much for the suggestion.
All right. Thanks for those questions, and thank you, Tarannum. And so, in the interest of time, we'll move on to our final presentation. Yasasi?
Thank you, Dr. Weigel. Let me share my screen.
All right.
I hope.
There we go.
Okay. Good afternoon, everyone. My name is Yasasi Abeysinghe, and I'm from Nerds Lab. Today, I'm here to present our research on advanced gaze analytics for distributed eye tracking, also known as ADC track. Before we begin, let me give you a brief overview to eye tracking. So eye tracking is the process of identifying the gaze location or a location where a person is looking at. So eye tracking technology has various types of eye trackers. So these eye trackers mostly generates a stream of eye movement data, and these eye movement data includes gaze points, which is X and Y coordinates of a screen or a place that a person is looking at, or the pupil dilation of each eye of the user. So these eye tracking technology, these eye tracking work that we have has multiple applications and research areas. One of the hot topics in today's world nowadays is using eye tracking in virtual realities and augmented realities. So we know Apple Vision Pro, Meta Quest Pro, these have eye tracking technology embedded within the virtual reality and augmented realities. There are other research areas in this, such as analyzing human visual attention or measuring the cognitive load during different tasks. For these, we can use eye tracking as well. One of the other applications is using eye tracking technology to test user experiences or user interfaces in different human-computer interaction applications. So, as I have mentioned, the advancement of eye tracking technology allows us to use eye tracking measures to understand human visual attention and human cognitive load. However, most of these eye tracking studies are single user studies, which means these studies are mainly at a given time, these eye trackers capture one person in an isolated environment. But a lot of the things that we do, most of the works that we do in daily basis are collaborative work across in online environments during COVID and even after COVID, meetings or learning like education work and then other collaborative tasks, they are happening remotely where people are distributed across multiple geographical locations. So having understanding how visual attention and cognitive load works for multiple people in this collaborative environment will help us to improve the user's engagement. But what we need here is to have a way to analyze the visual attention and cognitive load and these human visual behaviors in a collaborative environment. And for that, we can use eye tracking. The way to go with is using eye tracking or extracting eye tracking information from multiple users. So as a solution, we can use multi-user eye tracking. So multi-user eye tracking can be done as co-located or distributed. Co-located means the users are in the same physical location. In distributed eye tracking, what we can do is extracting eye movements or eye informations from multiple people who are distributed across multiple geographical locations. So to this end, in one of our previous studies, we introduced an architecture for distributed eye tracking called DIS-E-Track. So this DIS-E-Track system utilizes joint visual attention of users to understand their collaborative behavior in different interactive tasks. And there we visualize them in a dashboard. So, however, in that study, we only focused on basic gaze measures and basic pupillary information. But there are other gaze measures, advanced gaze measures, where we can use them to gain more understanding into visual behaviors. So we extend this DIS-E-Track system by introducing different, integrating different advanced gaze measures as well as traditional gaze measures. So we used two advanced gaze measures for now. One is real-time coefficient K, which is an indicator of visual scanning behavior. So how it works is it can say the fluctuation between a user's focal and visual ambient attention. If the user is very focused when they doing a task, or they are looking all around, like having a scanning behavior across the content of the screen. And the other one is real-time index pupil reactivity, which is an indicator of cognitive load. So these measures has been used in the literature, but mostly for single user studies. In this work, we are introducing these real-time advanced measures into distributed eye tracking setup. And then we visualize them in an interactive gaze analytics dashboard. We also improved this system's reproducibility by allowing users to restream this eye tracking data and then again transmit into a visualization dashboard. So this is the architecture of our distributed eye tracking system. It has two setups mainly. One is real-time distributed eye tracking system. Other one is data restreaming setup. So in real-time eye tracking setup, we acquire data from multiple users who are distributed in multiple geographical locations. And for that, we are using common eye trackers available in the market. And for acquiring data, we are using their vendor APIs and SDKs, and we transmit that data into an MQTT broker through a public network. In the data restreaming setup, we are allowing users to restream data that are restreaming previously collected eye tracking data. So from previous experiments, we can collect eye tracking data, and through this setup, we can restream it into the ADC Tracks dashboard. For this, we are using Streaming Hub, another tool that is developed in Nerds Lab. So in both real-time and also data restreaming setup, the data is transmitted into a MQTT broker through a public network. So this transmitted data include gaze X and Y coordinates of a user and also the pupil diameter of the user along with the timestamp and a user identifier. Then we are computing real-time gaze measures using RayMap API, which is another tool developed at Nerds Lab. So RayMap API, also known as Real-Time Advanced Eye Movement Analysis Pipeline, is an eye movement processing library that generates real-time advanced gaze measures as well as real-time traditional gaze measures. So as I have mentioned, real-time coefficient K shows the focal and ambient behavior of users in real time. And also RIPA, or real-time index pupil reactivity, shows the real-time cognitive load of users. The final component of our architecture of our dashboard is real-time visualization. So these advanced and traditional gaze measures that we have computed in real time are transmitted into a interactive gaze analytics dashboard in real time. So this is the layout of our dashboard. This contains tabs at the very top, allowing users to switch between different gaze measures. And as I have mentioned, the data is streamed into this dashboard in real time. So the proctor or the viewer of this dashboard, if they want to, they can play and replay, play or pause these data coming into the dashboard as required. So this is the visualization of the gaze measures. So in the bottom, there are gaze measures of two different users in different lines. And also we have aggregated, or it's a collaborative ambient focal attention, or the collaborative cognitive load is shown in the top. And finally, we have controls to zoom in and also save, reset the data or the visualizations. So this is the work that we have done so far in this work. I wanted to talk about the future direction of our work. So we are planning to expand this ADC track or our distributed eye tracking setup with advanced case measures into virtual realities. So virtual reality VR technology has an head-mounted display, or this VR headset that we have seen. It allows users to see the virtual world. And as I have mentioned, most of these consumer level eye trackers and also research level eye trackers as well has eye tracker or eye camera embedded within it. So it allows the VR headset to detect the direction where the user is looking at. So what we are planning to do, what we are trying to do in our current work is to extract these eye movement data, such as locations, and if the eye camera has the capability to detect the pupil diameter as well. So we are trying to extract this eye movement data from the VR headset and send it to our ADC track system, which is analyzing the real-time visualization, real-time visual attention and cognitive load. So we will be able to analyze how the cognitive load and attention works in a virtual world with this setup. So I would like to do a quick demo. So we do have a MetaQuest Pro. So I know compared to Apple Vision Pro, this one comes with controllers as well. And also, I think Apple Vision Pro, we have to use hand gestures to control the interface, but this one also we can do hand gestures, but it also have a controllers, but I feel like controllers make it very easy. I am not able to get most of the stuff done with the hand gestures, but that feature is available. So what I will try to do here is I will wear this and I will cast what I'm seeing into my computer. So you will be able to see what I'm seeing as well. So hopefully this will work. I hope you can see what I'm seeing. So this is basically augmented reality work. Like there is the lab, you can see it, but there are like interfaces that has that is in the world. So we can move it around, but again, I'm still seeing the real world, but the virtual interfaces, the virtual components are on top of the real world. So
yeah,
here,
Yasasi, can I ask are you holding things in both of your hands? Is that what the little light things? Okay.
Yeah, do you see the like a laser kind of things, right?
Yeah,
so that is
yeah.
that shows me to where to click. That is very useful like that. And also, I don't know if you can, if I put these down, yeah, I can use hand as well. If you can see, there's a cursor kind of a thing, but I just having really hard time finding the positions. I think it's very smooth in Apple Vision Pro. I haven't tried it, but yeah, I still can minimize it. I did that, but I find this more easy to use. I will show you a demo of and this is a VR app that is already in the that's something that I have installed. So this is a live on board on International Space Station. So the so here I can like look around. I have to stay in the boundary, but we can set stationary boundaries and we can set moving like a room scale boundaries as well. So there are a lot of applications with this. This is something we can use to train people. Like there are like for international space or other things, these VR applications are used to train and then give education in different ways. So yeah, once we are still working on it, but if we can extract these eye movements, these eye cameras, it's not usually eye tracking data is like X and Y coordinates, but here there's a depth coordinate as well, X, Y, and Z. So integrating these things and finding where the exact location user is looking at in a virtual world, we can gain insight into different things. So, I mean, yeah, this is the virtual reality of inside a space station. So there are different things, I guess. I don't know. I can't remember how to do that. Like, yeah, this one. So it has different things that we can do. Like we can have the instructions embedded in it. Like there are really cool stuff that we can do. Yeah. So
if you're around, you can always come by our lab
yeah.
and try this out yourself as well.
Yeah, there are other cool stuff as well, such as roller coaster. The games kind of they are roller coaster, but some stuff are making you dizzy as well. But you can come around and play with these things. And in the future, we are planning to show things that we develop, hopefully, so you can see how our work in a virtual reality world. So in summary, we introduced a distributed eye tracking setup with real-time advanced gaze measures and also traditional gaze measures. So we are using off-the-shelf eye trackers through a public network. And this, our distributed eye tracking setup allows users to gain insight into visual scanning behavior and cognitive load in a distributed environment using these advanced gaze measures. And we visualize this data through a interactive gaze analytics dashboard. In future work, we are working to integrate this with real-time virtual reality. So with this, I will conclude my presentation. Thank you everyone for listening.
All right, thank you. And kudos for attempting a live demo and succeeding. Does anybody have questions?
Not a question, but kind of a comment just to share, like, I mean, if there's any interest, Brewster, Hale, and Mark Graham especially, they are very interested in exploring these virtual reality options that are emerging into realizing them into, like, what would a library experience be like, where library being a digital library, the Internet Archive, if you are like just digitally with those headsets, like VR headsets and all, right? Can we go through it and just ask, like, hey, this particular section, maybe create a visualization or something, like, I mean, kind of a LLM generated illustration of something in the spot, or if you're reading a serious book, typing onto an entity and learning more about it, or if there's a citation of another book or paper, can we go jump there and find the right spot from there and then come back to what we were reading, kind of sort of moving these objects around, interacting with them, and kind of having like a more immersive reading experience. Again, I mean, I don't want to block anyone's thoughts around it, but it's kind of this what I heard them saying in a way. And if there are other interesting ideas that can be put forward in that environment, I think there will be people who will be interested in at the Internet Archive.
That sounds really interesting. Thank you for sharing that.
I have a question, and I was hoping you could
Ah,
clarify something for me. Basically, this is not my area. This was something I was hoping to work with Sampath on, but then COVID happened. Who is the target user for the Gaze Analytics dashboard?
So right now, I believe this dashboard mainly for targeted the researchers who already have some sort of a knowledge of these advanced case measures, because that's how we developed it at the moment. But if we can improve it in a different way, that a common audience can also, like people who does not have any technical background, and still, like, it's something that we have to improve, I guess, in the visualization aspects, so that they will know, okay, the high values of this thing means this is a high cognitive load, or in a different way. Visualization, I think that we can improve, but right now I believe someone who has at least basic understanding of these measures would be the audience right now.
So I'm just envisioning, like, you have somebody doing development on a system, like somebody at Meta or whatever, and they're evaluating a particular aspect of the user interface. And maybe you've already said this and I missed it. But the thing is that this can help them determine maybe a particular part of the interface that might be too difficult for people. Got it.
Yeah.
Okay. Thank you.
That would be the goal, I would say, when we develop, like, using some sort of objects in the virtual reality, and that increases their cognitive load. Okay, they have to do something with it, or there are a lot of research avenues, I would say.
So
that's really cool.
From the application point of view, something like teachers in a classroom. So, this may be a really good way for us to understand the way that we are teaching, and how the students kind of receive their cognitive load, and how we can kind of change the way that we are delivering the teaching, and the way that we teach something. That we get, it's why it's a distributed component right there, because we have a bunch of kids probably connected online wearing virtual reality headsets, and we are teaching, and suddenly we know that they're having a hard time understanding what I'm trying to say. So we can change that, and so that these data points will tell you, the instructor, like how to change the mode of delivery in real time.
Very cool. So are there any other time for, like, maybe one more question? Anybody else? All right, thank you. And so thank you to all of our speakers today. I did want to give the chance, I believe Dr. Ashok is here, and give him a chance to do a little intro. All of the WSDL faculty did a brief intro. So Vikas. Yeah.
Thanks, Michelle. Wasn't expecting that. So
sorry. On the spot.
All right. So hello, everyone. Those of you who are hearing me for the first time. So I'm Vikas. I joined quite some time ago, 2019. So I'm still an assistant professor in computer science department. So like Sampath, I also am associated with field of human-computer interaction mainly, but it's mostly human-centered AI. So I look at how we can use these recent, advancements in AI, particularly all this generative AI, large language models, and other NLP, build some kind of intelligent assistive technologies for helping people with disabilities, especially those who have visual disabilities, interact with digital content, including web, general desktop applications, mobile applications. And these days, I'm also looking at wearables and all these new tech. So that's my field of research. So yeah, Mohan, my student, presented earlier. So I also am looking at the privacy and security of people with disabilities online. It's a very underexplored topic. So looking at that. So other than that, I think I'll stop here. That's my quick intro. So
All right, thank you.
Michelle, you can, yeah.
So I'm gonna turn it back over to Dr. Nelson and let him wrap us up.
All right. Thank you so much. I guess we could do one more call for anyone that has something to share as far as opportunities, announcements. Are we good?
I've been trying to. Oh, sorry.
Please go ahead.
No. I've been trying to let you guys know about any employment opportunities or anything at Los Alamos as I find out about them. I'm noticing now that we're going through resumes from this side, instead of being a student trying to get a job, now I'm somebody who actually works here, like I wasn't before. I've started compiling a list of things I'm noticing. I'm thinking about putting that up on the wiki for you guys as it becomes more concrete. There's just certain little things that I'm noticing that tend to make people reject resumes or possibly ask more questions. So I think that would be useful. But beyond that, yeah, I'm just letting you guys know whenever I notice something's available. Let me know if you're interested. Some of you have already reached out to me. I've tried to find some spots for you at Los Alamos, but I'm still learning the process. So.
Well, thank you, Sean. Yes, please share this information with our group and with nobody else.
Of course.
Excellent. All right. Anyone else have anything to share here? All right, excellent. So just a reminder, at 3:30, we're going to meet at Hanks on Colley Avenue to celebrate Sampath's tenure. So if you're in the neighborhood, please stop by. Again, everything is on us, so don't worry about the tab, but we got you covered. Please come out. And getting tenure is a big deal, and we're very happy for them. And we've strategically placed it, so we'll have professors at each step, so we can do this as part of our annual experience. All right. If there
this is so unfair. I'm here in Paris, and you guys are celebrating, and 2 days later I'll be there.
Yeah. All right. Well, the celebration lasts a long time, so you can take Sampath out separately.
There you go. There you go.
All right. Thanks to all the presenters. Thanks to everyone who showed up, especially our alumni, the people, WSDL is for life, and we appreciate the dedication. And we'll post this video online in the near future. All right. Thanks, everyone. Appreciate it. Have a good weekend.
Thank you. Bye.
Congratulations, Sam.